Ended where we did a conversion of miles per hour into meters per second. This is the reverse. Meters per second into miles per hour. So it's not going to be that different, except that it's going to be different. We're starting with our meters per second here. 30 meters per second. Where would be a good place, like rather than going straight directly to miles per hour, what would make sense as a place to stop before meters per hour or even kilometers per hour? So we're gonna make a stop at kilometers per hour first before going to miles per hour, because miles is a completely different type of measurement, as we know. It's the English measure. So let's first make our goal to get to kilometers per hour first. We're going to use this factor label method, so that means we're going to be looking to cancel some things out. So if we work with our meters first, we're going to change meters into what unit? Kilometers, good. So how many meters are in a kilometer? 1,000. Remember, that's something I want you to have tucked away. That's one that's used many, 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 many times, even though you have your conversion table. I want you to know that 1,000 meters are in a kilometer. So 1,000 meters in 1 kilometer. You're really doing nothing more when you're converting these things than multiplying by ones. That's just the ones look a little strange. So this way the meters will cancel out. It's just ones. 1 kilometer is the same as 1,000 meters. So you're really just multiplying by 1. That's why this works. And then our seconds is going to have to get changed over to hours. So the seconds, will the seconds go in the numerator or the denominator for canceling out? Numerator. And what's going to go in the denominator? Hours. We want to change the seconds into hours. So how many seconds did we say were in 1 hour? Good. 3,600 seconds were in 1 hour. We did the calculations. But once again, that's something I want us to use enough that you know that there are 3,600 seconds in 1 hour. So where's the 3,600 go, on the top or bottom? Top. 3,600 seconds in 1 hour. So here is where our seconds are going to cancel out. So our unit is now kilometers per hour. And we have, our math will be 30 times 3,600 over 1,000. Okay, so 30 times 3,600 over 1,000. You can cancel out zeros if you want to make easier math, or you can just rely on purely your calculator on that. So let's do that math real quick. You guys should all have your calculators out. 30 times 3,600 divided by 1,000. That's what I'm seeing too. 108, what's my unit? Kilometers per hour. Now we're almost there. We have kilometers per hour rather than miles per hour. 108 kilometers per hour. Your speedometer, by the way, on your car actually usually has a place that tells you kilometers per hour. Mm-hmm. It's stupid things in the box. Somebody decided to get creative. I think they're cute. They're comforting me. So the kilometers are going to cancel out, and we need to replace them with, because we've got per hour, we need to replace them with miles. So we know that there's 1.61 kilometers in 1 mile. So what number goes where here? 1.61 goes which place? Bottom with the kilometers, 1.61, and the 1 mile on the top. So really, the math that we're doing is just dividing 108 by 1.61. Well, yeah, but that's not, you've got to get the 30 into its correct form first. So we are going to have miles per hour. How many miles per hour? So, who's got it? Not 93. I was counting on you. You have your calculator and everything. So did I. 67.08 rounds to 67 point, how much? 1 miles per hour. Now remember, whenever we have an M here, mph is miles per hour. If they mean to be meters, they use a slash. The English is the only one where you do the mph thing. It's just it's strange. And miles are very different than meters. As far as distance goes when you're figuring things out. So we want to make sure we're on target with that. All right, now 4 meters per second. Yeah, a little different. All right, now we're going to start going over quite a number of concepts, including those ideas of slope that was brought up yesterday. So it'll be quite a little bit of writing here so we can keep up with this. Okay. And I need to make some of these points really, really clear to you. Even though it may not seem like extremely important, we need to define an instant. Okay? An instant is a specific time, not a time interval. Okay? An object will be at a certain place at a certain time, okay, when it's moving. However, not through the time interval. Okay, there is a location that something is at a specific time, at an instant. But there's no length to that instant. Okay, so at 1 second on the top, at the 1 second mark, you are at that location. But you may not be there for a certain amount of time. You may not be there for any time whatsoever, but at that time you're there. And the next time at 1.2, you would be at a different location possibly. Yeah. Yeah. Yes. So at an instant is a specific time, not a time interval. So in the whole thing with dividing, if you think about it being at a specific time, we run into a divided by 0 problem in some cases. But we can talk about where something is and when it is there at that instant. Okay? An object can be at a position at an instant in time, but not for an instant. It sounds like a strange English lesson, but an object can be at a position at an instant in time, but not for an instant. An instant isn't a...
It's not a unit of measure.
Right.
5 instants ago.
Right, exactly. And it does get very specific in that. Once again, we have this whole divided by 0 thing we have to watch out for. We have to also, I'll just wait or I'll make it confusing. Okay. An instant has no duration. I'm saying the same thing over and over again in different words. That's not a length of time. An instant has no duration. So once again, not for an instant, but at an instant, you're at a location. Once again, there's no answer to the question, how long is an instant? Okay, like I say, I'm saying the same thing over and over again, different words. Hopefully that'll make a good point to you, and it'll all make sense. And it should hopefully make sense later as far as why we're doing that. Okay, not doing that. But a position time graph, here's what we're using it for. A position time graph shows the location of an object at different instants in time. So at the 1 second mark, it shows where it is. At the 2 second mark, it shows where it is. At the 3 second mark, it shows where it is. And then when you connect those points, those different locations, then we have something else to talk about. Then we can have our velocities and all those other things. It's not, actually this isn't d minus t, it's actually d dash t. Position time is designated as dt. When you see d dash t, That means position, time. D represents position. We had talked in other chapters about delta D representing change in position or displacement, but just a plain D represents position, T represents time. So D, T, position, time. It's a little bit strange. You would think it would start with a P, but it doesn't. D represents position, T represents time. And that will be a good stopping point for us for lunch. And fire for. Okay, so I've got some questions for you based on what you were doing with the work you were working on yesterday. We can begin to think about how these things would look. On a position time, remember we're going to use DT to represent position time. How does a DT graph usually appear if an object is in constant, positive, usually means forward, usually because if you wanted to, you could make backwards positive, but that would be silly, motion. So an object in constant, positive motion, what would the graph look like? Alvin, what are you thinking? It will be straight, but we need to think, is it straight on a slant or is it straight horizontal? Let's think about what that means. Positive, constant, straight on, what do you think?
Bottom left to top right.
Like that? Okay, that looks good. I'm seeing some visuals out there. Sorry you guys are not here to see it. Yeah, yep, no, I gotcha. So basically up and to the right. Positive, constant motion is like a positive slope on a graph, on a regular, normal graph that you're used to. So positive, constant motion is a straight line with a positive slope, up and right. And that's exactly what was being demonstrated. Can you stop doing that, please? Thank you. All right, so straight line with a positive slope, up and right. That would be constant positive motion. So what about that horizontal? What kind of motion do you think the horizontal would be if you had a horizontal line? You've got time not going anywhere. That's right. Good. So not going anywhere would be a horizontal line. We'll get to that one. It's not the next question I had, but that's going to be the third question. How does a DT graph appear or a position time graph appear if an object is in constant negative motion? Which would be straight line, negative slope, down and right. Good. Beautiful. Straight line, negative slope. So you've got to keep in mind when you've got those things, up and right does not mean northeast. Down and left does not mean southeast. Down and right does not mean southeast. It's a matter of positive and negative. It's that time axis. Okay, the time axis is what is the horizontal axis. So just don't get fooled by that. It's important. And then we said, how does it appear if the object is at rest? Good, a horizontal line. Straight horizontal line, slope of 0. I do want to start tying in that idea of slope, because the slope is actually going to show us where we're going with these things is finding some equations, and I'm getting all this information out so that you don't think the equations come from nowhere. The equations that we're going to be using in this course come directly from all the math that you've been learning in Algebra 1 and Algebra 2, little bit of geometry. So all these equations come from somewhere. And this whole idea of slope is going to be helpful in figuring all that out. Okay? So once again, if it's a straight line, positive up, we've got constant forward motion. Negative slope, constant backward motion. Horizontal line, nothing. No motion. At rest. And these are really super important concepts. Uniform motion is another name for that positive constant motion. Motion. Okay. Equal displacements happen during successive equal time intervals. That's just a long way of saying that you have a straight line or constant velocity. We all remember that slope is rise over run. That's nothing new. I didn't want to have all that stuff up there yet. Slope is rise over run. We know the slope formula. The slope formula is something very old. When did you start with that? Was that algebra 1 or pre-algebra even? Pre-algebra slope formula, y2 minus y1, x2 minus x1. So you could probably say that in your sleep. All we're doing is adding some words to it. Okay? On a position time graph, which one's your x and which one's your y?
D is Y.
D, good. D is y, t is x. Okay? So in our slope, we're going to have d's over t's. Okay? Straight line, same deal with the slope. But here we've got, instead of having 2's and 1's, we have 1's and 0's. So our slope is d1 minus d0. Wait a minute, we've seen that before. d1 minus d0, that is, that I think, displacement, yep. Displacement, you started saying it right, Alvin, good. So displacement divided by change in time. And here's that word you wanted, Alvin. What was that word? Velocity. So change in position divided by change in time. Slope, it's literally the slope formula. Delta D, there's your deltas. All we're doing is adding a little language and some different symbols. And honestly, when you go to college, I was helping somebody out this summer. They went and changed some of the variables on me. Why they do that periodically, I guess it makes them more money because they have to republish it in a different book. It doesn't mean that it's any different on the math side of things. You have to be used to looking at things. And if they change a variable on you, it doesn't change the math, just kind of, I mean, what they're trending towards, or at least what that book trended towards, was leaving it. Actually, they did a weird thing. They changed these D's into X's, which is the weirdest thing because now you've got X on the Y-axis. It was like really annoying more than anything. But, you know, kind of get used to the idea of seeing different variables in the different locations. So it's your same old slope formula. That's our average velocity. Okay. Now, as long as it's uniform motion, as long as it's a straight line, the average velocity is going to be the slope. But you could have 2 points on a wavy line, and you could find the slope between those 2 points, and that would give you an average velocity. Average velocity is only the actual velocity when it's uniform motion, or a straight line on the DT graph. Okay? Average velocity in general in life doesn't have to be the same as the actual velocity. Okay, so we've got an example graph here. Okay, one common mistake that people make is considering just d divided by t as being the speed instead of the slope of the line. Okay, be careful that you consider the slope as the average velocity, not just plain the position divided by time. Okay, because the thing is that you don't always start at 0. So some of you have already even calculated the equation of the line. That's very good. Okay, excellent. So you already would be able to tell us the speed, and you'd also be able to tell us where the thing started, and that's kind of where we're going on this. But I want us to really carefully consider this. The slope is the average velocity. It's not just position divided by time. Okay? I know that just came up there with a whole bunch of stuff all at once. But if you take any 2 points on a line, okay, we're used to that. We can calculate the slope. This is nothing new. Rise over run, 10 over 2. This is 2, 4, 6, 8, 10. Or 20 over 4 would still give you 5 meters per second. If I take the time to plug it into the formula, 40 minus 20 over 6 minus 2. 40, later position minus earlier position, later time minus earlier time. You still get 5 meters per second. That's the slope of the line. That's the average velocity, and it's actually the actual velocity as we go because it is a straight line. Now I said to be careful to consider the slope as the average velocity, not just plain the position over time. For example, at this point, what's the position of the object? What's the position of the object at 2 seconds? 20. Okay? So if you just considered it position divided by time, that would be 20 divided by 2. And that would be 10 meters per second, but that's not actually right. You didn't go 10 meters in 1 second. And if I did the same thing here, I'd have 40 divided by 6. And once again, that doesn't give me my 5 meters per second. That's actually the actual speed. That gives me an answer that literally means nothing because our motion didn't start at 0. So I've got all these things crossed out because we don't want to do that. Okay? We don't want to just take d over t. And yes, there will be a homework question that relates to that. And refers you to a picture that's on an actual separate page, which annoys me when they do that, and tells you to look. So what we're going to do now is we're going to stop, and you're going to work on your problems